Hello everyone, this is Arindam. How are you guys doing? It's been a while that I uploaded something, useful on this channel, something informative. So today is Sunday, it's weekend, and I was working on a project, and I, I was just, came across few interesting things, and I thought, why not share it on my channel if it helps anyone out there. So today we will be talking about LDA, that's linear discriminant analysis, not the LDA from NLP. So yeah, the LDA, which tags along with PCA. So basically what I want to discuss about today is not something something just like a textbook theory or something like that, or it's not something that you would find anywhere on internet, and that's why obviously I'm making this video. This is something you can actually apply in your real world scenario, whether if you're a working professional or someone working on a project, right? So initially I would just try to build up some conceptual foundation in this video, and in the end I'll give the useful tip that we can actually implement on our project, that will help us with better accuracy and better results. So yeah, please stay connected with me till the end, and let's get started, right? So before I jump into LDA, right, I want to speak about PCA, right? So I'll quickly just touch a little bit of PCA before I jump into LDA. What's PCA? Principal component analysis, right? So we'll just study this or just understand this enough to set the base, right? And then we'll move ahead. So what exactly is PCA? So it's basically a technique to reduce the number of features while keeping the important pattern intact, right? Again, so it's a technique to reduce the number of features while keeping the important information still intact, right? So many of the times you would think that the more number of features we have in our data, the better it is for our model. But sometimes what happens is, when you feed too many features into a model, things can go bad, right? And that problem is called the curse of dimensionality. So this topic, this terminology, curse of dimensionality, it's a very popular topic in the world of data, and it's a key concept. So if you know about this, then well and good, and if you are hearing it for the first time, then I do recommend reading upon it at some point of time, because it's really interesting to know how it works and why excess of dimensionality is bad for your data. Now we understood that having excess or too many features into a model can be bad for us. Now, how does PCA help? PCA helps by combining the most important information from your features and then creating a new compact ones. So let's say if you have got 100 features in your dataset, okay, PCA might cut that down to say 50, right? But still they keep the essence of the data, right? It will still retain the information of the data, right? So again, you have got, for example, you have got 100 feature in your dataset, right? Now I'm not gonna demonstrate how to code in this video, maybe later sometime I would, but see, you come at a point where you have to give the number of components, okay? So it's on us, okay? We have got 100 number of features. How many components do we want to take? So when it's time for me in the code, I can either give number of components that I want to take out of those 100 features. So if I put in 50, the PCA will give me 50 features out of 100, okay? But though that 50 features, I'm not sure what percentage of information that is giving me, okay? It is possible that those 50 features are just giving me 70 or 80 or 85% of information out of that 100% of data that's there, right? So that's one way, I can give that number of components that I want out of the total features that I have. Or the second thing that I can do is I can give the percentage of information that I want, and then the PCA will decide how many components it should be giving me. So let's say I give I want 95% of information, and I am ready to lose 5% of information from what I have. Then PCA will decide whether how many features it should give me, whether it should give me 30, 40, 50, 60. It's up to PCA. We will not know how many components, principal components that it's giving us, okay? So 95% of information, it can be transformed or shown in either 20 principal components, 30, 40, 50. It could be anything, we'll not know. But what we'll be sure about, that we have 95% of data with us, right? And we have just lost 5% of data, okay? Now what did I say? That we will be reducing the dimensionality and retaining the information at the same time, right? Now listen to this. So there are other ways to deal with this curse of dimensionality as well, and it's just not PCA that will be helpful. There are other ways as well, okay? So the other few fixes are like hyperparameter tuning, which you must be aware that we use when our model is overfitting, right? So we go ahead and use hyperparameter tuning, right? Then we use VIF, which is variance inflation factor. What does this do? This is really helpful when we are dealing with multi-collinearity, right? When our input columns or input features are too much similar, right? Then we use VIF, variance inflation factor. Then we have recursive feature elimination and many, right? And the last one is, using tree-based models. So this is, you must be aware that tree-based models are pretty robust. They are built strong. They can handle outliers. They are not sensitive to outliers. They can, they're very strong and complex built, right? So these tree-based models like decision tree or XGBoost, gradient boost, right? So they have these inbuilt feature selection method, right? So they automatically pick useful features. Okay, so these are the 4 methods that you can remember: hyperparameter tuning, VIF, variance inflation factor. Then you have got recursive feature elimination. Then you have tree-based algorithms, right? So these are the 4 fixes of curse of dimensionality. Now, what happens when you use these 4? Okay, these methods. So these techniques drop the unnecessary features, okay? And when you drop those features, what happens is you are losing the data. Okay, you're just deleting or dropping the columns, right? And with that you are losing the data as well. But with PCA you're not dropping, you're blending, you're combining the columns and then creating new ones which are much stronger and much good and better, which means that there is no loss of data, right? So this is an important distinction that we should remember. Now, these fixes either can be used alone without using PCA. We go ahead and use these 4 methods that I spoke about, or we can also use this along with PCA. Okay, so let's say I went ahead and I did the process of PCA and still PCA, and then I applied the algorithm, and then my metric score was not as good as I expected, right? So what I would do is I would go back, run these 4 fixes, check for multicollinearity, check for overfitting, all these factors, and then again run my PCA and then run my algorithm and check the metric score and see if there is an improvement or not, right? Also, a key point to remember is that just PCA will not help. You need to keep in mind what algorithm you are using after applying PCA. If the data is not linear, but you're going ahead with a linear algorithm and you're expecting a good metric score, then that's somewhere you need to keep a check on. Okay, so if you're not using tree-based algorithm where for a classification data, or where you have a lot of outliers, and you're not using tree-based algorithm, then you need to keep a check on that. You need to use tree-based algorithm at that point. For linear data, you need to use linear algorithm. Okay, so it's very important the selection of algorithm that you're going ahead with after applying PCA, right? So again, either you can use these 4 fixes alone, or you can definitely use them along with PCA as well. So there are no restrictions that if you use these 4 methods of to fix the curse of dimensionality, you cannot use PCA, or if you're using PCA, you cannot use these four methods. There are no restrictions as such, right? Now let's move ahead and understand working procedure of PCA. Now, so we were gonna discuss how the PCA actually works and what's the working procedure of PCA. So I have gone ahead and just try to draw something. Just give me a moment. Yes, pardon my drawing, but yes, this is the best that I could. So yes, let's see here. Right, now this is PCA part, and we'll discuss this later, right? So think of it this way, so you have plotted your data points, right? And you have in PCA, what exactly happens is you create a new axis through your data. You're seeing this. You have a new axis line that passes through your data, right? Now this axis line, okay, remember this, that this axis line is not a decision boundary or a best fit line, like you might be thinking, or if you have studied the concepts of machine learning algorithms, then do not confuse this axis line with the decision boundary or the best fit line. Okay, decision boundary is something that's created in the classification models like decision tree, XGBoost, and logistic regression, and models like this. Okay, whereas your best fit line is used in the linear regression, which is not a classification model, but a continuous model, right? But yes, this is to tell you because PCA is not an algorithm, right? And this new axis line is not to be confused with decision boundary or best fit line. Now what happens is, when you pass this axis line through your data points, okay, then these data points are actually projected on the new axis, okay, to give you a transformed version. Okay, so this one gets projected on this line, this one gets projected on this line, and goes on. And after transformation, you have a single dimension, one dimension of data, and all your points are lying on that one single line. So this is how I'm just obviously we cannot plot more than 3 dimension either on the code or the script, or on the board, right? It's something that can be done by the ML models, even they do not visualize it, so it's all mathematics running behind. But just for the demonstration purpose, I've taken 2-dimension data, and then I've plotted the points over here. So to understand, we pass a axis line through our data points, and after transform, and all these data points are projected on the axis line to give us a transformation data, right? To give us a transformed version. So the same idea is applied on LDA, which we will see later, but this is how it works. This is the PCA. This is the dimensionality reduction process. Okay, now again, this access line, the PCA creates multiple tens of hundreds of access line, and then one is selected out of all those after comparing. So basically, how it works. So again, this is not a best fit line, but this does work on idea of best fit line. So let's say I pass one access line. Okay, now this access line, the best access line is the one that is closer to all the data points in the data set, in your records. Okay, and the same thing goes with best fit line, but this is not best fit line. Okay, so even this works on Euclidean distance idea. Okay, same like best fit line, but this is not best fit line. And when you pass and you compare all the lines, whichever line is the closest to all the data points, that particular line is chosen to be the access line. Okay, so again, the access line is created by both PCA and LDA. In PCA, the data points are projected on the access line, and then this gives us a transformation, gives us a PCA transformation, and that looks something like this on a single dimension. Okay, now we know about the access line, and it's used both by PCA and LDA. So let's go ahead and move to LDA part. Now, so LDA, so there are situations when PCA will not work even though it is classification data, right? So you're seeing this, the second row that I have shown. Just we have seen PCA, and in the second row we have got some plots over here. Okay, so as I said that there are scenarios when PCA will not work even though if it's a classification data, and then that is when you have something called as inseparable classification data, right? So you're seeing that this is inseparable classification data, and by the way I have did this, or the way you would see anywhere, this is what your inseparable classification data would look like. So obviously it'll be much more messy when you work with more than 2 or 3 dimension data, and this is just for illustration purpose, right? Because obviously we cannot plot more than 3 dimension data. So nevertheless, we have got an idea how inseparable classification data looks like. You're not able to have a separation space, or you're not able to classify which one is what, right? Which data point goes to which class, and so on, right? One data point is overlapping another one, right? So these are the things, right? So we have got an idea how inseparable classification data looks like, and if you have such data, then even the machine learning model cannot build a proper decision boundary, and it gets difficult where the decision boundary should be. Okay, even if, let's say, I go ahead and apply PCA, I go ahead and draw a access line, passing through this, then obviously, our decision boundary would be incorrect. Our metric scores and predictions will be very much wrong. So it will make no sense, right? Now, as we had discussed that LDA does work like PCA, as mentioned, it uses the access line, right? New access line. But there is a catch. Okay, so listen to this. When LDA was designed, right? So its main purpose was not to reduce the dimension. Okay, so rather its main goal was to separate data or transform data in such a way that the data is separable, right? So again, the LDA was designed not to reduce dimension, but rather to separate data or transform data in such a way that the data is separable, right? So it separates the inseparable data, but because it uses the access line, the dimension reduction takes place automatically, right? So you can say that LDA separates the inseparable data, and because it uses a access line just like PCA, as a side effect, the dimension reduction takes place automatically as a side effect. Okay, now coming to a very important point, right? And it's interesting to know that how the LDA decides on its axis, right? Meaning which axis it should be selecting, the best axis for LDA, what's it's gonna be, right? So in LDA, the axis line that's gonna pass through the data should follow, or rather I say should meet two criteria. First, minimize the variance within each class. Second is the distance between the two mean of each classes should be maximized. Okay, again, the variance or the spread, right? The variance or the spread within each class should be minimized, should be as less as possible, and the distance between the mean of two classes should be as far as possible, should be as big as possible, as maximum as possible, right? And these criteria take place simultaneously, right? So minimize the variance within each class and maximize the distance between mean of each class. Okay, so I have just drew these two plots to try to demonstrate the two criterias. So if you see, this is the spread of our green data points, from here to here, that's a spread of green data point, and here to here, this is spread of a red data point. Now let's say I want to minimize this. Okay, so I would go ahead and compress this portion, this thing that we have. I would go ahead and compress it so that I minimize the variance, I minimize the spread, and just visualize that if I go ahead and compress it, I squeeze this. Okay, don't you think that all the green data points will start coming closer to each other, right? And parallelly, I am doing the same for the red data points. I am compressing the variance, I'm squeezing this, and all the red data points are coming closer to each other. Ultimately, there will be a point when they would look something like this, right? You would start seeing a separation when I minimize their spread. So we are minimizing the variance. We are ultimately creating a separation space, right? So they are getting closer, right, to each other each, and then you can actually make a distinction, right, that hey, I can see one class here and another class here. So that's the benefit of minimizing the variance or minimizing the spread. Once we have the separation space, we can definitely have a decision boundary drawn from here, right? Now the second criteria, right? So imagine having a mean point in this cluster, in this messed up data points. I mean, even if you find the mean of red data points or green data points, okay, how far would they be? The mean, the distance between those two mean, how far they would be to each other? Definitely not as far as this much, right? Because mean of this is this over here, and mean of the red data points is somewhere here, and the distance you can see is as maximum as it could be. But if you compare to its previous version, right, the mean would be, this distance between two means would be not obviously as far as this. It could be here and another one here, and the distance between the two means would be very less, right? So obviously when you have these two criterias meeting, right, the axis line, then you can have a decision boundary passing from it, right? So these two criteria is must. And remember, if you're going for an interview or anything like that, then this is a very important 3 points that you should remember for LDA. That's it works on inseparable classification data. It uses the concept of axis line just like PCA. Its a main goal is to separate the inseparable data, right? And the axis line should meet two criteria: minimize the variance within each class and maximize the distance distance between each mean of each class, right? So these are 4 to 5 points to conclude about the LDA that you should remember, right? Now the next thing that you should remember, or you could think of, is when to go ahead with LDA. And now we will discuss about few important tips and tricks that one should go ahead with when using PCA or LDA, right? Okay, now the main question arises is when to actually use LDA and how to know data is actually inseparable classification or not before you actually jump to do LDA procedure, because it's actually time-taking process. You would not want to waste your time without actually knowing whether you should go ahead and do LDA procedure or not, right? So to conclude, okay, to know whether you should go ahead with LDA or not, there are 2 points, 2 tips that I can suggest if you're working on a project is, right, first is if you're working on classification data, right, so whatever classification algorithm you're using, right? Logistic decision tree or random forest, anything, whatever you're using, or whatever algorithm that you're using, irrespective of the type of data that you have. First, train the data without dimensionality reduction, and then check the scores. Okay, if your metric score, is poor, then understand that decision boundaries may have, hard time being formed. Okay, so obviously if you have balanced data, then you would go ahead with accuracy score. If you have imbalanced data, you would probably prefer ROC score, right? Then you have your confusion matrix that you go ahead and assess. But as per these scores, you would definitely come to an understanding that my model is not performing well. And if it's not performing well, then do understand that your decision boundaries are blurry, are not being formed well, right? So that's step one. Now, to make sure that your step one is actually valid and verified, do this. Use a clustering algorithm, be it like k-means or agglomerative clustering in hierarchical. Okay, I would suggest use these clustering algorithms. Okay, apply these on your features and check the sellout score. Okay, so obviously sellout score, if you're it's near to 0, then you would definitely come to an understanding that the clustering is not being done well. And if the clustering is not being done well, that means the data separation is not proper, right? It's a poor separation, right? So these two things or strategies you can apply. Okay, first, never use dimensionality reduction in the first go. Okay, first check your scores of your algorithm without using dimensionality reduction. Then if it's poor, check use a clustering algorithm. Even if that's poor, then definitely we can come to an understanding that okay, my data is inseparable classification data, right? So this is all that you can come to an understanding, that check these points. If you get to know that okay, this is an inseparable classification data, I'm gonna go ahead and apply LDA on this, right? And in the last, if still nothing is working out, then third point that you can this is optional, but this helps sometimes, that you can also apply PCA before applying LDA. So what it does is basically PCA will remove the noises that are there, and then you can apply LDA. So this is very rare and optional, but you can still go ahead and give it a try if nothing is working out. Okay, so this was all about PCA LDA, working of PCA and LDA, and then when to actually go ahead and use LDA, because nobody will tell you whether you should go ahead and apply LDA or not. You cannot just go ahead and blindly apply it in your project. It's waste of time, waste of your resources. So you have to use them wisely. Okay, so these checks are important, right? And I found this one website. Okay, this is really interesting. I will, and if you want to know about the formulas, the working of the new axis line, basically the formula behind this is the z-score. Okay, so you can give a read about it. It's really interesting behind the axis line. So I'll share this in the description, and if anyone has any new idea, or if they are working in any project, or if they want to point out something interesting that's they think is you know could be correct in my video, then do get connected with me on my email, or you have if you have any interesting idea, do get connected to me on my email, or on my LinkedIn, and we can discuss things further. Right, so this was it. Have a great day. Take care.